we going to be talking about today?
We are talking about free fall.
Free fall. So when something's dropped, basically?
When something's dropped, when it's freely falling.
Okay. So like that lab we did.
Exactly.
You know, I had a question about the lab. When we had the crumpled up paper and the flat paper, they're both paper, but they didn't land at the same time. That's pretty weird. Why did that happen?
They were both paper. They were both the same size. You squished one up, but you have to think about the surface area, because as something falls, we have air particles in our air that is pushing up on these two objects. So the one that has the larger surface area is going to be slowed down by air resistance, which is a force that pushes up.
So when I take like a piece of paper and I crumple it up, I'm losing the surface area.
Yes.
Okay.
Because look, surface area here, large, small.
Okay.
More,
so it's gonna
more area for the particles to push up on, so it slows it down.
Okay. That makes sense. So what about like if we had, you know, a bowling ball and a feather?
Bowling ball and a feather. Well, because of the force or the acceleration due to gravity, if you drop them both at the same time in a vacuum, they would hit on the same time at the same time because you don't have any air particles slowing them down as they fall.
What's a vacuum?
A vacuum is an area that's absent of all air particles, all matter.
So it's like nothing.
It's nothing. It's just a nothing.
Do you think we can find a clip of that?
I think we could.
Okay, let's watch it right now.
Okay.
Okay, so that kind of makes sense. So why though in real life is the feather float down? Is that the air resistance again?
You do have air resistance.
And the bowling ball lands sooner?
Yes.
Okay. Interesting. Well, I know, Ms. Shep, that you love to make me do math problems.
Math is fun.
Okay, so...
Math and science go hand in hand.
That's okay. Get out your packets, guys. All right, so... it says Chuck Upton is riding the Tower of Power at Fiesta, Texas. If Chuck free falls for 2.6 seconds, what will be his final velocity? What are we going to do, Ms. Shep?
We need to use the acceleration formula.
Okay, how do you know that?
Well, let's look at what they give us. They give us time.
Okay. Time, oh, that's the seconds, 2.6, right?
That's all right, 2.6 seconds. And they...
That'll give you a pen.
Oh, there we go.
Okay.
And it's asking for final velocity.
Okay, I don't know initial velocity.
Well, he's free falling, which means at the very top, he has 0 meters per second. He's not moving at all.
Oh, okay.
So we're going to put that in for our VI.
Okay.
So let's go ahead and plug in VF with the question mark.
Okay.
And then VI is going to be 0.
Okay, I don't know acceleration or time, or wait, no, acceleration or distance.
Okay, well, acceleration is due to gravity. So that's going to be our constant of 9.8 meters per second squared, and since we're falling down, we're going to show our downward direction with the negative sign.
Snap. You got me. All
There
right.
we go.
So distance we don't care about.
We don't have that yet.
Okay.
They're not asking us to solve for it, and they don't give us distance.
So we need the equation without distance.
So we need, oops, that's a V. This equation.
Okay. So then can I just, I'm not solving for A, that's a little bit confusing.
Okay, so we need to rearrange our formula.
Okay.
We are actually solving for VF, so we want to rearrange so that we have just VF on by itself on the other side of the equal sign. So what we're going to do, if we've subtracted VI on the right, we're going to add it on the left.
Okay. Do we need to get rid of that T first?
We can do that now.
Okay.
Let's start over. Let's get rid of the T first. So we need to, since we divided by T, we're going to multiply it by it on the other side.
Okay, so I have A times T.
A times T. So
and that cancels, right, on the right?
That cancels on the right,
okay.
And we're bringing it over to the left. We multiplied by it on both sides.
Okay.
So now we have T times A equals VF minus VI.
Okay.
And then...
Now we can just add VI.
Now we can just add VI. So
okay.
if we add VI on this side, we got to do the same on the other side. It's hard to write that. Okay.
Okay.
So now we can just plug in what we have. VI we know is 0.
Okay.
A.
That was negative 9.8.
Hold on. We have T. We have
okay.
T. Sorry, my pluses and my T's. So 2.6, and I'm going to put that in parentheses just to keep it straight.
Okay.
And then A is our negative 9.8.
Okay. Well, the 0 just goes away, so all I have to do is multiply that, right?
Uh-huh. So this goes away, so all we do is multiply those two numbers, and we get negative 25.5.
How can velocity be negative? That still is confusing me.
It's all about direction
Okay.
because we're falling down.
Okay, so falling down, it's going to be negative. Okay.
Yes.
Can I show you another way to solve
Sure.
that?
One thing I want to show you with units real quick, because we have second squared on the bottom and seconds over here, this goes away, the squared goes away, and we're just
Oh,
left
that's
with our
tricky.
meters
So
per
that just
second.
helps you. Perfect. Okay, so let me show you another way. So we already have, let's see, let's get my eraser going here. I'm going to keep your givens because we have to go through the guess method every time anyway.
Okay.
But I kind of like to just go through with the numbers in there already. That rearranging by the letters is confusing sometimes. So I'm going to show how I would do this. So we still have the same equation. Okay, but now I'm going to just go ahead and plug in first and then rearrange. So I have negative 9.8. I have VF minus 0, and then over T, which is 2.6. So now I can multiply by 2.6 on both sides, and it's going to cancel, and I get negative 25.5 meters per second equals VF minus 0. Well, that's just going to go away. We don't even care about that.
Well, there you go. Same thing.
Cool.
Awesome.